all right? So when we look at a probability distribution for that, well, we can't have negative height, right? And we, you know, if we measure, let's say in feet, okay? So let's say like 5 foot here, this is foot, and then let's say 6 foot here, right? You get the idea? Whatever. See, with rolling a die, there's only 6 outcomes, right? But when you're talking about people's heights, we can start measuring, and we're not going to have like just 5 foot, you know, right? You could have like 5'2". You could have, if you want to get to decimals, it could be like 5.729 feet, right? And so you have all these gaps in the middle that could actually happen, couldn't they? As opposed to here, where it's either you roll a die, it's either 1, 2, 3, 4, 5, 6. When you have events that occur that can only take on integer values, this is called discrete probability or discrete variables. Anyone take statistics? Okay, these are called discrete random variables because they can only take on integer values. And so to look at areas, it's very easy because we just create these little rectangles. But when you have what are called continuous random variables, where you can take on any value in between, then you can't draw rectangles anymore. But there is a probability for each thing. It's like, what do you think the probability is if this is 1? What's the probability that some human being, if you measure their height, is 5 foot? Pretty good? Pretty bad? What do you think? Pretty good, right? I don't know, 60%, 70%, who cares, right? Somewhere around there. What's the probability that they are 1 foot tall? You could have a little baby, right? Right? But, I mean, you could have some probability, right? What's the probability that they're 6 inches, so half foot? I mean, so now what we're getting at now are very small probabilities, right? Yeah. Very small. So you get smaller probabilities here. Now, what's the probability that someone is like a person's 1 inch tall?
That's like Ant-Man.
Now, I mean, we're talking. Can you say 0? You can't say 0, and here's why. Because you can have a probability of a person being 1 inch tall that is so infinitesimally small that it's still a positive number. What do you think is more likely? A person being 1 inch tall, or what do you think is more likely? A person being 1 inch tall, or me winning the lottery every single day of my life for the rest of my life, and also being struck by lightning every single day of my life for the rest of my life? Which of those? Okay, so we could argue, right? You could argue like which one's more likely, but do you agree that me winning the lottery every day of my life for the rest of my life and being struck by lightning every day and surviving, that it could happen? It could happen, like it could happen if I played the lottery, right? So but we're talking about infinitesimally small probabilities, but it's greater than 0. It's greater than 0. See, people lose sight of the fact that you can have a number that's greater than 0 that's so small that it's irrelevant, like it is almost 0. So what we have here is like an asymptotically approaching 0 function. All right? And then over here, we got 5 foot tall, whatever. We got some people who are 6 foot tall, whatever. And then you start getting the 8 footers. And then you start to drop down again to infinitesimal, right? We don't have 10 foot people. What we need with probability distributions is the exact same thing that we have here, which is that the total area under the graph must be the sum of all the probabilities, right? That means the total area under this has to be 1. Agreed? But it stops here at 0, but it goes in that direction forever. Now, what's the probability that you have a 200-foot person, right? Infinitesimally small, but it's greater than 0, right? So in the real world, in statistics, we want functions that behave this way, that have a nice number answer, even if you're going out one direction forever. Because you have to account for all those very crazy probabilities. And the function we just had, right? This function we just had is almost a perfect probability density function. Almost perfect. Except for the fact that the answer is 1. I mean, sorry, it was pi, right? And we want it to be 1 because we want it to represent all the probabilities. So we could easily fix that by just putting a 1 over pi out here. Now the area is 1, right? The area of that's 1 now, because this is pi, and that's going to be 1 over pi, so you get 1. So there are very important functions in math that when you look at the areas under them, they give you 1. And the one that you're most familiar with that you didn't even know was the standard normal bell curve. You know the bell curve, you've seen that? It's called the standard normal distribution. That function that they're using, the area under it is 1 in both directions forever. Okay. I hope that that's somewhat, in some way. Oh, you know what? One more thing. Sorry. If you're looking at a continuous variable like this, like the height of someone, if you ask what's the probability of somebody being 5 foot tall, you cannot come up with that probability with a standard, with a continuous variable like this. It's not like rolling the die where you can get like what's the probability of getting a 4. It's impossible to talk about the probability of an event at a single value when you have something like this. So what you have to do is you have to look at the probability of this value being between two things. So that means maybe I say between 5 foot and 5 foot 1, because then I can actually calculate that area, and that area is the probability. Just like that little square on the, or little rectangle on the rolling of the die, the area of that was the probability of it happening. The area of this little sliver would be the probability that a person is between, let's say, 5 foot and 5 foot 1. But it's impossible to talk about what's happening exactly at 5 feet, because then you don't have area. You just have a straight line. All right. I'm on topic, but off topic. All right? Why don't you do that one? Let's do some classwork. All right. Pardon it? If that's what you want to do. Yeah. What I'm looking for most here is, of course, that you're doing the right thing. But work on your notation. Like your limits need to follow you the whole way through until at the end when you actually take the limit. Okay, so work on good notation here and splitting this up properly. All right? Go ahead. Enjoy. Y'all can work together. I'm not going to collect it. This is really just for fun.
It's like almost like setting up two limits.
All right, are y'all ready to talk about this? So let's discuss this. So first of all, we're going from negative infinity to infinity, right? So we're going to break it up into two integrals. I'm going to go from negative infinity to 0, and then 0 to infinity. I could have gone negative infinity to 1, 1 to, it doesn't matter, right? Any number in between. Agreed? Okay, so then each of these is a limit. This first one, I'm setting up this limit as t goes to negative infinity. I replace the lower limit of integration with t. Top one is still 0. Then this one, another limit. I replace the upper limit of integration with s. I let s go to infinity. Same integral. Now, I have to find the antiderivative of this. So over here on the side, because, again, integration by parts, that's correct. We're going to have to use that for this one. I just do this as scratch work on the side. So I've got my u and I've got my dv. So I come down, I take derivative here, I take the integral here, and then we get ultraviolet minus integral voodoo. The integral of this is just e to the x. So this is the antiderivative of x e to the x. We okay with that? Now that goes and replaces the integral signs, right? But we still have limits there. So it's like I'm going to do this, I'm going to do that, and I'm going to replace all my x's with 0, then all my x's with t, all my x's with s, and all my x's with 0. So first I plug in 0 here. For all my x's I get this. Plug in t, I get this. Next limit, plug all my s's in for the x's, plug in all my zeros. We good there? Okay, now let's see what happens. What does this become? Negative 1, minus 1. So that's 0, right? But e to the 0 is 1, so minus 1. Yes? while we're there doing that, this one's going to become minus 1 again. All right, so that's what happens here. Ready for the next part? See what happens as t goes to negative infinity. T is going to negative infinity right here, right? Right here. I think it's worth us talking about that over here on the side. I'm trying to take the limit as t goes to negative infinity of the expression t e to the t minus e to the t, right? That's what I'm trying to figure out. All right, so let's take a look. This is Cal 1, all right? T is going to negative infinity, so that goes to negative infinity, right? So this is what it looks like. I have this going to negative infinity, and then this one is headed where? Be very careful here. So do you know what e to the t looks like? Well, do you know what e to the x looks like? That's e to the x, right? So let's just call it e to the t. That's e to the t. What happens as t is going to negative infinity on that graph? You're headed to 0. That thing's headed to 0, isn't it? So this is headed to 0. So what you're getting right here in this first part is this, and then you have minus over here, e to the t again. Well, we just did that, right? That's going to 0. Cal 1. What happens when you take a limit and you get infinity times 0? It's indeterminate form, and you have to still do something. So L'Hopital will work, but L'Hopital only works if you have infinity over infinity or 0 over 0. We don't have that. We have multiplication of infinity. Is everyone clear why this is indeterminate? You have one number that's getting big, right? And one number that's getting small. We're not saying that this is 0, are we? We're saying this is approaching 0, this is approaching infinity. Take a big number, multiply a big number times a small number, who wins? You don't know, right? You need to know how big they are. So here's how we could do this, all right? I know my Cal 1 students, this may ring a bell. If you have infinity times 0, you always take one of the functions and drop it down into the denominator. So now, do you all understand I don't need to worry about that anymore because that's going to 0? Yes. Okay, so I'm really looking at this. Limit t goes to negative infinity of, I'm going to do it this way. It doesn't matter which one you drop, but I'm going to leave the t on top, and I'm going to drop the e to the t to the bottom, which makes it e to the negative t. Very important that that's a negative t now. So I've taken a product and I've turned it into a ratio. Yeah? That's something over something now instead of something times something? But it's the same thing? Yeah. Let's just check real quick what happens. If t goes to negative infinity, my top's going to negative infinity, right? The bottom, because this is negative and now that's negative, two negatives mean positive, so it's going to e to the positive infinity, which means we're going this way on the graph. And that goes to infinity. So essentially I have like an infinity over an infinity here. And when you have infinity over infinity, you can use L'Hopital's rule. So L'Hopital's rule, I know the book does it different. I know that other teachers probably do it different, but I always put an L over my equal sign to let everyone know I'm doing L'Hopital. I think most books do an H instead. Whatever. Limit. What does L'Hopital's rule tell us we can do? If we have infinity over infinity, we can do what to this? Take derivative of the top and bottom separately. So what's derivative of the top with respect to t? 1, and derivative of the bottom with respect to t, be careful. Negative e to the negative t. Now, let's run the limit again. Let t go to infinity. You no longer have anything up here, right? So the top's headed to 1. The bottom is negative, and then e to the negative infinity, which means e to the infinity. And e to the infinity is headed to infinity, right? So the bottom is becoming infinite. And what happens when you have a fixed number over something becoming infinite? It heads to 0. So this limit is 0.
So how do you make t equal
How do I make t be positive infinity? Oh, okay, because this is negative, right? But I'm replacing t with a negative infinity. Oh, that's just properties of exponents. So like, you know, if you have like x squared, right? That's the same as 1 over x to the negative 2. Like you can always take something and drop it down. I can always take something and drop it down to the denominator and change the exponent to a negative. That t? This one. Why is that negative? Oh, that's this one.
Yeah, but that's negative infinity.
Yes. Okay. Well, oh, I'm sorry. Yes, that is negative infinity. Is that what you're saying? Yes. For L'Hopital, it doesn't matter if it's positive or negative infinity. We just have to have something infinite over something infinite. It can be plus or minus. That doesn't matter. Is that what you're referring to? Yeah. Sorry. Technically speaking, yes, that's headed to negative infinity over infinity. But for L'Hopital, you could go plus or minus doesn't matter. Just has to be infinite over infinite. All right. We good there? We have another one to do. And we have to do this one because, look, check this one out. S is going to positive infinity. That's different than negative infinity. It's the same expression, but we're going to positive infinity. So I'm going to do that over here.
Sir, we have a quick question.
Yes.
So in the end, when you like let it go to infinity,
Yes.
so you have negative.
I let it go to negative infinity.
Yeah.
Uh-huh.
So you have negative e to the negative t, and how do you get positive?
Negative e to the negative t. Okay, again, I'm sorry. It's negative infinity.
Oh, okay.
Yeah. Yeah, because that's a negative out here. This goes to infinity, right? That goes to infinity there? Okay. The fact that it's negative doesn't change the fact that this goes to 0. Sorry, I should have been more clear about that. Because I guess what you should do is go back and think. I mean, you might have to review this part of Cal 1 a little bit to go back and think about what it is we're trying to achieve. If we ever see fixed number over infinity or negative infinity, it doesn't matter. If the denominator is becoming infinite, regardless of positive or negative, and the numerator is fixed, that thing goes to 0. That's it. That's all we care about. So I should have been more specific. Yes, that's a negative, but at the end of the day, it doesn't change anything. Okay.
That doesn't matter only when we're using the L'Hopital's rule, right? Everything else, I mean, we have to consider negative infinity and positive infinity, right?
I didn't care about the negative here because to use L'Hopital, I don't care if it's negative.
Yeah, only for L'Hopital, right? I mean, everything else we do have to consider that positive or negative infinity.
In general, yes. The reason I didn't care about it here wasn't because of L'Hopital. The reason I didn't care about it here was because it's a fixed number over something infinite.
It goes to 0.
And that goes to 0, regardless. All right, so let me try this second limit right here, this one. S is going to go to positive infinity. We have s e to the s minus e to the s. All right, let's talk about what's happening here. Are we going to need L'Hopital's rule? Let's see. This is headed where? Infinity. And I'll be very specific. Positive infinity, right? Times e to the infinity really means like look at the graph of e and go out to infinity and it's going up to infinity, right? So that's infinity also. Then we have minus. Now this one is also what? Infinity. So what's infinity times infinity? Infinity. Minus infinity. What's infinity minus infinity? Indeterminate. Infinity minus infinity is not 0. It could be. It might turn out to be 0, but it's not in general. It's something that's becoming very big minus something else that's becoming very big. You have to know about how big it's getting, how fast it's getting big in order to come up with an answer. In Cal 1, we should have seen that in this situation, sometimes one of them dominates the other one. Sometimes they compromise and they settle on something in between them. It just depends. So how do we deal with infinity minus infinity? We still do something, right? We do something. You always try and factor first if you can. You try and turn this subtraction into a product. And I think you can see that I could have factored an e to the s out right in the beginning, couldn't I have? If I factor an e to the s out, then what would I get? These both have e to the s. So I'd have that and then s minus 1. Now just run the limit again. Just run the limit one more time. This piece is headed where? Infinity. Times, right? That's times. Now what's this headed to? Infinity minus 1, which is still infinity, right? Now you have infinity times infinity, not subtraction. And two big numbers multiplied together is a big number. So this becomes infinite, right? Which means that this goes where? Infinity.
So why did you decide to drop the e to the t on the last one, but not this one?
Because we were going to negative infinity.
So if it's going to negative, then you should put it
No. It's whatever happens when you take the limit.
after you take
The reason I dropped, in the last problem, the reason I dropped it is because when we did this part, we didn't have that. We had 0 times infinity.
Right.
Or we had infinity time, negative infinity times 0 or something like that. And whenever you see 0 times infinity or 0 times negative infinity, the standard practice is to grab one of the functions and drop it.
Okay. So in this case, because it's
In this case, because that didn't show up, we didn't need it. What we did get was this, and the standard practice for that is to factor.
Okay.
And so we factor, and voila, it works out real nice. Now, all of this work, yes?
So if you get, like you said, infinity minus infinity, or infinity plus infinity, you have to start over.
No, infinity plus infinity is infinity.
Only when it's minus, it's not 0. Okay, so infinity minus infinity, it's not 0, so we have to start over and then factor that. Is that what you're saying?
Yes. You know what? I know what you're looking for. You want me to help you like have sort of like what you do in each case. I can't do that in 3 or 4 minutes because it's like several days in calculus 1. So what I can do is maybe look back at some of my videos from Cal 1 and I'll maybe send out an email to the whole class. Like if you want to review indeterminate forms and L'Hopital's rule, here's some videos you can watch. I can do that because it's, again, even if I told you what the rules were right now or what to look for, you still have to go practice them because it's in practice that you start to really see how these things work. Is there another?
No, I changed my mind.
Okay.
But basically, it's just safer to factor from the beginning, right? That way you will get a product.
I guess. I mean, I don't know if safer is the word. Factoring is something you could have done, so yeah, do it. I mean, doesn't hurt if you're stuck and you can't figure out what's going on, try factoring it. Yeah. All right, we haven't answered the question though. All right, so look, if we come back and look at all this, this was going to a number, right? -1, and then we have -0, right? So this is, so far we have convergence. All right? Even over here, we have +1, which looks like convergence, right? But this piece right here is infinite. And so it doesn't matter if we add 1 or subtract 1. If we have infinity and then these other constants, this thing is becoming infinite, which means that this integral diverges. It diverges. And it's all because of this right here. It's all because of that one right there.
So let's say on the test we get to this.
Uh-huh.
Can we just put divergence? Or divergence?
Yeah, if you write this line right here and you show, but look, here, you need to show this, all right? So like you need to somehow, you can't just say, oh yeah, that's infinity.
Yeah,
Like you need to show that that's infinity somehow.
that second line of what-
Then you can say divergence. Yep. Maybe put a little arrow to that and say this integral diverges or whatever. Okay. So that's part of why we did limits with all that stuff in Cal 1. That's part of why, because you need it for these sorts of things. Not anymore. You don't anymore. No, you don't. It's all in your head. Oh, hey, look at this. I didn't even, I forgot I put this in here. This is the standard normal distribution. So this looks crazy. I know this looks crazy, but everything in here is a constant except x, all right? So this is a constant. You know how when you're talking about like standard normal, they tell you about like the mean, the average, and then the standard deviation. So like if you know the average, which is this one right here, mu, and then the standard deviation, and you plug those numbers in, then this is an exponential function. Just ignore that for now. Do you agree that this is e raised to like something with x in it squared over a constant? So this is basically an exponential function that has different things, like you're scaling it, and there it is right there. Whoa. There it is right there. Now if I change my mu, I can move my average. So if you're talking about like heights of people, your average is going to be, you know, somewhere around 5 foot, somewhere in there. That's your average. If you change your standard deviation, you can make it, it's probably more like this, right, in the real world? Like a lot of people in here, like not many people at 10 feet tall, right? And then you can change your R. Your R also has an impact on, you know, changing the width of the graph, if that makes sense. Yes? Yeah. Okay, so if we were to have a computer take the integral of that function up there from negative infinity to infinity, I typed it all in here for us, then the answer is 1. So the total area under that graph is 1. It turns out, though, it kind of sucks that this function cannot be integrated with any technique that we have. There's no integration by parts, partial fractions, trig sub, none of that works on that function. You can only do it with a series, chapter 8 later. All right, so a nice formula. And this we'll end with this. I know y'all ready to end a long time ago. But you know how I started the class with integral from 1 to infinity of 1 over x squared dx? And then the next example we did was integral 1 to infinity of 1 over x dx. And I showed that this one converged and this one diverged. Both of these are power functions where you have 1 over x to a power. Like in this case, you have 1 over x squared. Here you have 1 over x to the first power, right? And this is a formula that if you have an integral from 1 to infinity of 1 over x to the p being the power, then as long as the p here is less than 1 or equal to 1, see that's 1, right? So if it's less than or equal to 1, this thing will diverge. If it's greater than 1, it will converge. So let me show you how this works. If I do this integral right here, just tell me real quickly whether or not that is convergent or divergent. That's divergent because p here is what? 1/2. And so it's divergent, right? Now, what about this one? That's convergent because p is what? 3 over 2, 3/2, right? This is the same as x to the 3/2. So p is 3/2. 3/2 is bigger than 1. So this would converge. Now, it doesn't say what it would converge to, does it? It just says that it will converge. So later on, if we ever run across a problem, like in chapter 8, this will happen, where we will be actually using this for something. We're like, oh, well, that's just that's that p is greater than 1 that converges, right? So we're in business. We don't have to check it. Now, this note says that we need to show this is true. Now, I can't show it's true in 4 minutes. Bonus. If you can prove that that's true and turn that into me next class, then I'll give you a bonus.
Prove that what is true.
No. Okay, so the way that I would approach this, okay, it's great that y'all have Google these days, but it's also like bonus questions are kind of a joke because I'm sure you could find this somewhere. I would rather you actually try this. What I would do is set up the integral. Okay, so go and do this. Right? Go ahead and break it up. Do a limit, right? And leave p as p. All right, just let p be p the whole time through. And then when you go to take that limit, when you're trying to figure out what happens is you let t go to infinity, you're going to see that what that limit does depends on what p was. So don't replace it with numbers. Just leave p.
Until like later?
No, you'll never replace it with a number. Nope. You're going to get, at the very end of all this, you're going to get a limit. And that limit's going to have t's and p's in it. And so you'll look at that limit and you'll be like, okay, t's going to infinity, but I'm not quite sure if that goes to 0 or goes to this or whatever, because I don't know the value of p. But then you'll say, wait a minute, if p is bigger than 1, then I can say it does this. And if it's less than or equal to 1, I can say it does this. Look, it's a bonus, but don't go replacing p with any numbers. Because just because if you show it's true for 2 different numbers, that doesn't prove it's true for all numbers. It's a bonus, you know. All right, homework for this. I almost got out of here. You almost got out of here. Look, by the way, we're halfway through this section. Because remember, there's a type 2. Type 2 is a little different, as we'll see. There it is. So 1 through 31 odd. I don't know which problems you can do or not do. Just, I'll tell you this. When you're looking at the problems, if it says like from 0 to infinity, if the limits of integration have infinity in them, try them. If they don't have infinity in them, leave them alone for now. Is that clear? No? That's not clear? Look at these problems. Any problem that has an infinity here or here, anywhere, try it. If these are numbers like 4 to 7, skip it. All right, look, it's all cleared up. You can... Rain went away. Scared it out of here.